In this video, we're going to look at a set of data. We're going to fit a line to this data. So we'll have to graph it, draw a line of fit, write the equation of the line, and we can use this to do some interpolation and some extrapolation. In order to graph this, I'm going to first look at what are my x values. And my x values are going to go, and look at my smallest x value is here at 60. And my largest value is going to be at 70. So if I'm thinking on the calculator, that's going to be my x minimum. This is my x maximum. I'm going to think about this when I'm drawing my graph, in this case by hand. This is also kind of looking at what is my domain. Now, my domain is going to look at values from 60 to 70. I also am going to look at my y values, that's my range. And my y values are going to go, let's see, we go down to 27. And my biggest y value is 45. So that would be, in other words, my y minimum and my y maximum. So when I set up my graph, I'm going to have to be going from 60 to 70 and from 27 to 45. So let's take a look and see what that graph looks like. So as I graph this, again you see on the x-axis, I put this little mark here to say I'm going to put a break in the graph. So I'm going to start here at 60 instead of going all the way to 0. But from 60 I am counting consistently. I'm going 60 up to 70. I did a little bit more here. Same thing on the y. I put that break so I can start counting at 25. I went up here to 45. Plotted all my points. And I can see the points do look like they pretty much line up in a line, although they're not a perfect line. This looks reasonable to represent with a linear equation, with a line. So we will draw a line. Lining up my straightage on this graph, I drew in this red line. Now it looks what looks reasonable to me. If I look, I have 1, 2, 3, 4, 5, 6 points above the line, 1, 2, 3, 4, 5, 6 points below the line, and it looks like 2 points on the line. I don't really care if I have any points on the line. It looks like about splitting in half, about half above, half below. I look like I'm going about in the same direction that the dots are going, so it looks like a reasonable line. At this point, I don't really care about any of the data anymore, so I'm going to get rid of it. Once we've drawn this line, we are representing the data with this line, so this is what's most important. As I look for writing the equation of the line, I'm not worried about the points that I plotted. I'm just worrying about what is on the line. So I'm going to use point-slope form. The reason I'm going to use point-slope form is since I did these breaks there, I do not have the y-intercept. I don't know where the y-axis is. The y-axis is actually somewhere off this way, a long ways away, since this is only 60. I need to get to 0. So, let's pick 2 points on this line. So I think I'm going to pick this point right here. This is the point 70, 45. And I'm going to pick some other point that the line goes through. This one looks reasonable right there. This is 64, 34. In this case, they happen to be points I plotted. It doesn't matter if it's a point I plotted or not, as long as it's on the line. Using these 2 points, I'm going to find my slope. This one, I think, since I have the graph, I will just draw ahead and do a slope triangle. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6. So my slope is going to be my change in y over change in x, in this case, is going to be 11 over 6. And that's my b value. For my point, let's see, 11 over 6. For my x1, y1, I can pick either one of these points or another point that's, as long as, again, it's on the line. I'm going to take that 745. So my equation is going to be y equals 45 plus 11 over 6 times x minus 70. I can rewrite that into intercept form, either or by distributing and simplifying it, but this is good enough. This is a line. This is the equation of this line. That will represent the data. That's the equation we're going to work with as we do our interpolation and our extrapolation. Using our equation, first thing I'm going to do is find y if x equals 62. So I have the x. I'll just plug that into my equation. I get y equals 45 plus 11/6 times 62 minus 70. And if we plug that into the calculator, we're going to get y equals 30.3 repeating. And if we look at our graph, that looks reasonable. That's right here, a little bit over 30. Now you notice, it's not either of the points that I graphed for 62. I don't care about the points. At this point, I'm representing the whole thing with the line. Points don't matter. So this is my prediction. Now this is in a case of interpolation. It's interpolation because we're internal. We're inside the data set. If I'm looking, again, when we go back to that beginning when we were setting up the graph, we said all of our points were between 60 and 70. And so when we're looking for any prediction values inside these values between 60 and 70, this is my interpolation. And if you notice, it's pretty close to what our data said. If we have a reasonable prediction line, our interpolation is generally pretty close to the data set. So we're happy with that. Let's find another value. So let's look and see what is the value of y if x equals 20. This I definitely can't see with my graph, so I'll plug straight into my equation. So I go y equals 45 plus 11 over 6 times 20 minus 70. I plug that in, and I'm going to get y equals a negative 50.3 repeating. Now again, if I look at my original data set was going from 60 to 70, this is way outside of my data set. So this is in a case of extrapolation. We've gone extra. We've gone outside. So, how good is this prediction? That's something we don't know. Extrapolation, again, is not as predictable as interpolation. The interpolation, we feel pretty confident. With the extrapolation, we have to look at our experiment. We got to look at what the data is doing to say, do I think that's a good value for 20, or do I need to collect some more data? At this one, these points look pretty reasonable, so I don't have a reason to expect it to change, but I don't know.